Hello friends, welcome to PansimTech Private Limited. So today we are going to discuss about derivation of momentum equation, that is our second part. In our last video we have discussed about derivation of continuity equation. So in this video we are going to see derivation of momentum equation, and we will see how we are getting Navier-Stokes equation from that momentum equation. So before going forward, so let's introduce something about PansimTech Private Limited. As I am telling that we are basically engineering service provider in CAE. So CAE comprises of CFD, FEA, thermal, as well as we are doing product development, CAD CAM, verification and validation, virtual prototyping. So these all term you hopefully understood from our last video. What are these terms? And so we are also doing some academics and corporate training, mentoring and staffing, etc. So without wasting our time, let's move forward. So what is our how we are getting momentum equation? See, so what is momentum equation? So as we know, Newton's second law is what? So rate of change of momentum is nothing but impressed force, right? So F equal to ma. A is what? In terms of linear, V minus U by T, we can call it A. So mv minus mu upon T is your net change in momentum with respect to time is your force. So what are the different two source of force for any this is general. So generally two types of force we can see on a on a body or control volume. So this is control volume, you can see it from here. So body force and surface force. Body force is what? Body force may be, it may be weight, it may be electromagnetic. And what is surface? What are the different surface force? So pressure force, viscous force. Viscous force, again, it may be normal stress, or it may be tangential or shear stress. So you can see it from here. So these all are tangential stress, and if it is acting normally, it will get normal stress. Okay, so if you can see from this picture, so if suppose this is one face of the control volume, so this is in z direction. So if my pressure force is acting it here, so if I am considering change in momentum, or maybe we can say change in momentum in x direction, how we can calculate? So different what I am doing exactly, different forces we are calculating on this body, and that net force equal to m into a. That is our momentum equation. So we are going to apply same Newton's law of momentum into this equation, and we will see how it will reflect in fluid mechanics or CFD. Okay, so let's go forward. So if you will see here, so what is body force here? Body force is nothing but total volume of the body. So that means dx, dy, dz in x, y, and z direction, and into density. So density into volume is what? Mass flow rate. And if you're multiplying into this in gravity direction x, so you can get it weight in x direction basically. So what is this? Fx is nothing but is a function of dx, dy, dz in x direction and into rho. So this is your body force. Now net surface force in x direction. So surface force, as I told you in last, surface force in x direction is what? Change in pressure force plus what? Shear stress. It may be shear stress. So Txs is what? Tau xx means shear stress in x direction. Okay. So now how we can calculate this term? As if you remember our continuity equation, I already mentioned that portion how we are getting total derivative. So dou x equal to what? Sorry, delta x equal to what? Dou x by dou t into dou t by something. So whatever we are multiplying it denominator, we are cancelling it from in numerator. So something like that. So if you will see it here, so whatever is the final change in pressure by minus initial is your change in pressure in x direction. Similarly for shear stress, final shear stress multiplied by area minus initial shear stress multiplied by area. So this is your stress force. So if you will see P minus P plus dou P by dou x into dou x. So this is your pressure into area is dy dz. As we are moving in x direction, so dy dz will be area of this face. So plus, and this is your what? This is your stress in x direction for this phase. So stress will be total, on each phase where we are seeing both stress we need to take care. That means this is normal stress, this is tangential stress. Okay. So this is the tau xx plus tau xx by dx in. So in x direction, we are seeing change in stress here. Plus, you can see here in y direction also stress is happening. So stress we have to take in all directions. So this you can see x, y, and z direction from here. So everywhere we are taking this stress, and after that, if you will do means if you are opening this bracket and cancelling out everything, so how it will get, how it will come? So force in x direction is nothing but what? Body force plus surface force. So what is the body force here? So body force is this one. So this one is body force plus what is the surface force? Total is this one is the surface force. So tau xs is what? Shear stress in x direction, tau yx in. So this is all component. So x component, y component, and z component for particular x direction. Okay. So if we are what we can say now, can we say like force in x direction should be equal to force mass into acceleration of x direction? So can we equate these two? Obviously yes. So you can see it from there. So after substitution, what you will get? You will get like this. So similarly for y and z direction, you can get like this. Okay. So if you are dividing this all by d, means you can take simply common dou x, dou y, dou z, that means volume. So what is the force per unit volume? This you can get it from here. So dou u by dou t. Why we have written so dou u by dou t equal to this in x direction, y direction, z direction. So this is a summary of this equation: x momentum, y momentum, and z momentum in simplified form. In non-conservative form, this is the value. In conservative form, this is the value. Okay. So if you will see for new, so just substituting our standard equation for Newtonian fluid. You know that Newtonian law of viscosity. What is that? What is the Newtonian law of viscosity? So shear stress is proportional to velocity gradient. Okay, and that is your. So we are substituting that into the same equation, and what we are getting? So tau x is what? So this is what? This is your viscosity coefficient. Sometimes we can say kinematic viscosity, sometimes we are dynamic. So this is your dynamic viscosity or molecular viscosity. This is your viscosity coefficients tau. So if you are substituting these terms into this, so you will get like this. In x direction, this is the shear stress. This is the y direction. This is the z direction. Okay. Now, if we will again suppose in xy term, you will get like this type of equation. Okay. And so after substituting all this equation into the main momentum equation, you will get Navier-Stokes equation like this. So see, what is the Navier-Stokes equation from the momentum equation? So this is the x momentum equation, dou y by dou rho. So substituting this equation, so this is the pressure force, this is the viscous force, and this is the body force, and this is the with respect to change in momentum with respect to what? Time, correct? So and this is your del operator. What is the meaning of this del operator? You can see it like I hope you remember our last video. So del means what? I into dou x dou y. So this is vector calculus. So this is mathematical term. Please remember your basic mathematics. So as CFD is related to numerical schemes and as well as mathematics. So mathematics should be strong. Okay. Now if you will see here del. So if we are substituting this value, we will get the same equation, x momentum equation in our last slide, like this. So this is standard form of that. If you will substitute all values in the momentum equation that originally we got, so you will get this type of equation. Okay, so this is your local acceleration, this is your convective acceleration. I already mentioned what is local, what is convective. So with respect to change in space coordinates, that is your convective. With respect to time, it is locally. I have given one example also, that a girl is standing on the window. You can see our last video. So this is your pressure pressure force. So why negative sign? Adverse pressure gradient, this we can call it adverse pressure gradient. So and if you'll substitute that value, tau x value here, so you will get this equation. And if you'll again expand this equation, you will get more. So see, conservative form. So this is our main equation in x direction, this is your y direction equation, this is your z direction equation. Okay, so this is all about our governing equations related to momentum. Okay, as I told this, we are also providing some corporate and academic trainings. For detail, for getting certificates, etc., you can contact us. And also we are executing some R&D projects. We are already associated with various companies, so maybe you can call us with this on this number. And I hope this video you like. So please like and subscribe our channel, and so that we can get our more visibility. Okay. So thank